See a single slide? Okay. I see a lot of old friends on the screen tonight. Some of you have heard about this gift. Others have perhaps not. So I'm going to go through a couple of slides just to fill everyone in on the 32, where it came from, what it is. And the real topic of the night, though, is going to follow with a description of what it can be, which I think is as exciting uh, as anything else going on at CAC right now. Midsummer, we received a call from a defense contractor that had an offer that we couldn't refuse. And that offer was to gift us a DFM 32-inch Cassegrain telescope. It is a research-grade instrument, quite large, remanufactured in 2018 and sold to this contractor who bought it for a project that they were demonstrating capability for, but never got the contract. So we went up and picked up this telescope that is a quite sophisticated instrument. Instruments like this are all over the world at institutions. They are, this manufacturer has put telescopes at Kitt Peak, all over the place. And so here we are with an extraordinary gift. It's got some quite extraordinary benefits for TAAA. It is an instrument that will be able to be used by members. It uses the SkyX as part of its operating software, which many of you would know. It is a very impressive telescope. When you stand next to it, you get the sense that this is not the average amateur club telescope. We intend to put it at CAC. CAC has got a wide range of instruments that members can use there, from a 9 1/4 that we've just installed and we'll be doing training on, up to a 40-inch Dob that is quite an extraordinary instrument itself. TAAA is ready for this kind of instrument. We have got experience in our group. Unlike most amateur groups, we have got true amateurs to true professionals and all in between that have pitched in to make this organization what it is. And it makes accepting a telescope like this, putting it in place, and doing the things that we are considering doing to it, which you'll hear soon, quite possible for us. We have, at the same time that we received the telescope, the contractor required us to also accept the dome that this telescope was destined to be in. It's a 16.5-foot ash dome, which we determined was too small to accommodate the needs for TAAA. The telescope fit in the dome, but it just barely fit. And for some of the things that we want to do, hosting visitors, for instance, it just wasn't possible. So we've looked at various designs for an observatory, and we've settled on a roll-off roof observatory that will look something like the picture here. This is one of our members' observatories. The observatory is now being drawn and evaluated by a structural engineer, and we hope to have drawings that'll be able to go to contractors and to the county for permits by the end of this month. We're looking at the telescope use actually in 3 phases. The first phase is to build the observatory, get this to the point where we can install the telescope in the state that we picked it up, get it operating, run a period that we'll be able to use it and get a sense of what it can do and how we're going to manage this this wonderful instrument. Then we've got thoughts about phase 2, which is to take this telescope and reconfigure it. And I will save that here for a moment because Doug is going to talk about those possibilities. And phase 3 is to make it ready for remote operations. Now, I say that is phase 3, but I will tell you that in phase 1, yes, phase 3 is in our thoughts. So all of the things that we are putting into the design are being considered in terms of what will this look like if we go to remote operations. So we are trying to make it remote ready, if you will. To give you an idea of what the project looks like on financial paper, we expect that the total cost of the observatory is going to be $75,000. And since September 1st, we have been soliciting help from the membership to make that $75,000 goal. And to date, we've done pretty well. Members have either pledged or donated cash totaling $57,000, leaving us $17,000 yet to realize in order to make that goal of 75, be able to put the observatory up and in place. So we're doing well. If any of you before the end of the year find it in your hearts to make a donation that'll still count for the 2023 tax year and can take advantage of the match that we have right now. We have a $10,000 match that is drawn some donations, but there's still room for someone to contribute and get their contribution doubled by this match. There's also a footnote on this slide, and that is that we have that 16 and a half foot ash dome that was put on Astromart this weekend. That dome has already attracted 3 interested parties. So we will see. The board had agreed to accept that dome knowing that we would not use it, but expecting that we'd be able to sell it. It has never been assembled. It is in many parts because the original skids that they came on had to be unbundled in order to put this in a storage unit at the contractor. But we got all the parts. So we are looking to put that out into the marketplace and see if we can't raise, hopefully, enough funds to put us over the top there. So that's the background of this extraordinary instrument. It's going to be at CAC with a portfolio of other instruments. These other instruments, as most of you who are familiar with CAC know, are visual instruments, many of them quite extraordinary visual instruments. But we have no dedicated imaging scopes. So as we were considering what this telescope might mean to that portfolio of telescopes there at CAC, Doug Summers began a review of what might be possible with this telescope. And there are some particular design features that are different, that allow or disallow some particular types of configurations. But I'd like to turn it over to Doug and give him a chance to excite you with what might be possible.
Okay, so I'd like to share my screen if I can. Can I do that now? Let's see. Looks like maybe I can. Can you guys all hear me? Hello?
We can.
Hello.
Okay, great. Terrific. All right. Let me get to slide view. All right, can you see this first slide?
Yep.
Great. Okay, so I'm happy to share some thoughts about the 32. As some of you know, I volunteered to go up and be part of the party that went to Colorado to break this telescope down, primarily because I had heard about the telescope early, and I wanted to get a good look at it, just so that I could figure out what it is that the group was receiving and just sort of start thinking about it. I've done a lot of visiting of CAC over the years, and so knowing that I was going to CAC and my background as it is, I thought it would make sense to take a good look at that telescope and see what options were available to maximize that gift. So a little bit of briefing context here. I'm going to go through these slides relatively quickly. I recommend that this is supposed to be a summary. So if you get lost, we'll have time for questions afterwards. But if you do get lost, I recommend that people go back and look at the recording of this video, because the charts, if all of the detail in the charts don't make sense immediately, if you go back, you probably can make sense of it by just stopping on the chart and taking a look. So about this briefing in particular, I'm going to start out as a negative Nelly, okay? I'm going to try and convince you for a moment that an F13.6 telescope is a little bit of a dinosaur, and it's not intended for amateurs or amateur sites, okay? And then I'm going to pivot after I give you some of that kind of feedback. Then I'm going to pivot to the question of, well, if that's the case and it's not great as it is, what reconfiguration options might provide a better fit for CAC and a higher value to TAAA? And I want to emphasize here, okay, that this brief is an exploration, all right? In the end, it may have nothing to do with what actually happens with a 32-inch telescope. So this is just exploration, and people should use that as such. Okay, so let's start this whole discussion with the idea of using the telescope as is in its F14 state, if you will, using eyepieces, okay? And think about what kinds of challenges are going to happen there. Well, the first thing I'm going to tell you is that CAC seeing, which is basically 2 arc seconds plus or minus, all right, is not going to support a focal length of 11,000, all right? That kind of magnification is going to make objects appear really large, blurry, and dim in your eyepiece. You're going to wind up with a small field of view, okay? We're talking galaxy-sized field of view with your largest eyepiece, okay? So instead of having a portfolio of eyepieces, you're going to have to find the largest eyepiece you can get and then stick with that one eyepiece, and you'll see why in just a moment. This problem turns into kind of the equivalent of magnitude versus surface brightness. As you magnify everything really big, the objects become dim. And there's not much you can do about it because you're at the highest millimeter eyepiece that you can bring to the problem. If you try and go smaller eyepieces, the magnification problem gets even worse. So The other issue is that extended deep sky objects, things like nebula, they're going to get clipped. That's going to force you, if you want to look at those objects, to slew the telescope. And that's not really tenable when you're talking about people looking in eyepieces. So some people might think, well, okay, maybe planetary would be a great use for this telescope. And it might seem appealing, but the magnification is still too high. And minimally, I think you'd probably want an aperture mask to cut down the number of seeing cells, which I calculated for a 32-inch aperture, probably is going to be about 50 air cells moving on that mirror. You want to have an aperture mask there to mask that down and get to maybe 3 to 7 air cells, and that's going to give you a more stable look at the objects. But another problem you've got is the physical mount geometry, and it's not user-friendly. And what I mean by that, and I'll show you a picture of this, everything from zenith to the north, okay, on both sides of the horizon, east and west, might need to wind up being a keep-out zone. And if that's true, then you're kind of limited in your viewing to only 1/2 of the sky, everything south. In the end, I'm going to tell you that F-13 telescopes are not made for visual use. They are designed for instrumentation. That is a camera, a spectrograph, or a polarimeter. They're not made to be looked through. And I think we're going to see that in just a moment. So let's look at some examples of what I'm talking about here. Suppose you walk up to a telescope and M51 is in the eyepiece, and you see that they've magnified M51 to fill the eyepiece. What would you expect to see? This is 275 power at 40 millimeter eyepiece. So that's a wide field eyepiece, 275 power already. Don't think about how bright this looks in this simulation. Look at how big the object is in the eyepiece. And when you see it this big, you can assume that it's going to be dim. The reason why you do this is if you stretch the area, you're spreading that light out over a bigger and bigger area, and the object gets dimmer and dimmer. Yeah. So this object is going to be, because it's F13.6, it's going to be 7.5 times fainter than what you would see in the same size aperture at a faster focal ratio. So that's not really a great look. And there's nothing you can do about it except go bigger. Maybe you put a 55 millimeter eyepiece on there, but you certainly couldn't go smaller or the object will get bigger. Here's the problem with clipping. If you try, this is the Trifid Nebula. If you try and put the Trifid Nebula in, this is the same 40 millimeter eyepiece, 275 power. All you're going to get is the very center of this nebula. And we all know that there's a whole reflection nebula that's sitting outside of the center. And so this is where you wind up having to slew if you want to see any of the other parts of the nebula. And the Trifid Nebula is not that big. If you want to put on a bigger nebula, it'd even be worse. Here's a look at planetary, and you might say, wow, that looks great, okay? Well, don't think about the clarity in the simulation, okay? Because seeing is not gonna allow you to have that. This is what it looks like in a 13 millimeter eyepiece. That's a medium power in most amateur telescopes, okay? But that's 850, all right? So we all know that 850 isn't gonna work. In a 40 millimeter, the disc will be smaller, but you're still at 275. And let me remind folks, for those of you who were with us at CAC, during the open house, we put 275 power on Jupiter in the 9-inch refractor, and it was too much. Okay, so sight seeing plays a role here. You really, 275, that's a lot of power to put on a planet. And when you throw in an aperture of 32 inches and all those air cells moving on it, this is maybe not the greatest use for the telescope either. Okay, so now to this visual mount problem. So you can ignore, in the picture on the left, you can ignore the cart, okay? The cart at the bottom is not going to be there. But imagine you're in the dark and the telescope is at the zenith, under the telescope. And as you come down to the horizon, like the picture on the right-hand side, everywhere you move northward off the horizon, the situation gets worse and worse. Here's the person standing here. Imagine that person with their head and their body between the forks to try and get up in the middle of this telescope so that they can see the eyepiece. Personally, I think that's untenable. I don't really think that's good for both the telescope or for anybody else. And so, it's likely that everything north is unviewable with this telescope. I think that south is probably all you're going to get. So you have 2 quadrants of the sky, but you're giving up half the sky. Okay, so let's switch gears for a moment and talk about photographic use, all right, as is. If you were to go out and get yourself what I consider to be relatively large pixels, 5 microns, okay, you're going to have a plate scale that is 0.1 arc seconds per pixel, okay? That means that in 2 arc seconds of seeing, your stars are going to be 400 pixels, all right? That's way oversampled. Nobody would do that. The field is still really small, 11 arc minutes by 7.5 arc minutes. And that means that you're going to be doing lots of panels for mosaics if you want to do an extended nebula. At f13.6, you're going to be doing long integrations, which is really inefficient. And what I mean by that, okay, is if you think about the instantaneous signal difference between an f13.6 telescope and the same aperture size, but f3.1, it's 20 times different. That means that if you had an f3.1 telescope in the same aperture, you could take 1/20th of the exposure time and get, the image that you would get with a 13.6. So from an efficiency perspective, f13.6 is not really great. I want to say that I hope this is painfully, Captain Obvious here, okay, that imaging systems should be designed, okay, to factor the site characteristics. If you don't factor the site when you put together an imaging system, you're not going to function optimally. And this is kind of the story of what we've got going here with this telescope. All right, here's what I consider to be a good amateur view. This is M16. Pillars of creation are right in the middle, really small, okay? But this field is a little over 1 degree by a little less than 1 degree, and that's a good amateur field. In the 13.6 mode, you wind up for looking at the pillars, but again, they're going to be dim and blurry, and so again, you've got 1/10 of an arc second. This is with 6 micron pixels, by the way. Okay, so that's not really where you want to be. So hopefully I've convinced you a little bit, okay, in just a few minutes, that both visually and for imaging, f13.6 is not really where we probably want to be. Okay, so let's pivot now and talk about what makes the telescope f13.6 in the first place, and can it be altered to be more useful? So this is the layout of the telescope. This right here is the primary mirror. It's got a hole in it, okay, for the light to come through. And the light side, the sky side, is over here. Light comes into the telescope, bounces off the primary mirror. Whoops, I'm sorry. Bounces off the primary mirror, hits this convex secondary down the primary baffle and to Cassegrain focus over here. If this secondary and this focus mechanism were not present, light would come straight off the primary and it would form an image out at prime focus. Okay, this is prime focus. And if by chance you change this secondary to put an elliptical flat in here, you would fold the light path and you would come up to Newtonian focus. All right, so hopefully that's obvious to everybody, and that's where we're going to kind of spend a little bit of time. Okay, so what is making this telescope f13.6? Well, it's certainly not the primary, because this is the specs from the vendor for the primary mirror. You can see the figure is a parabola at f3.11. Now, we haven't tested the optics. We don't know what kind of quality the optics are. But assuming the optics are decent, f3 is a great foundation to build a telescope from. The telescope is f13.6, so that tells you that it's the secondary that's causing this problem. All right. And what you can think of this secondary mirror as providing built-in magnification at the expense of field size and brightness. Stated another way, you can think of this telescope as an f3 telescope with a permanently mounted 4.4 times Barlow, okay, that you can't get rid of. And this is part of the problem. So what if you could pick any focal ratio you wanted, all right? I put together a table here so that you could kind of play this game out in your head. And f3.1 is the bottom because that's our primary mirror. You can't go lower than that. The primary mirror is f3.1. f13.6 is the primary with the secondary. And so everything in between might be up for grabs. If you had a preference, what would you pick? And what I would suggest that it doesn't take very long to look at this table and realize, going to the far right, that the brightness and the signal, the multiplier from f13.6 down gets better and better, far better, with faster optics. The typical field size also gets far better with reduction in focal ratio. And the magnification gets a lot better as well as you go down from 13.6 to 3. So for your budget, okay, you should try and go as low on this table, that's my assertion, as you possibly can. All right, so I'm going to work with that for a moment, and you can come back and look at the video and play these numbers out in your head to see what you would prefer. But for my money, going down is better. Okay, so before I got involved in the project, I understand there was a conversation with the vendor, and the vendor suggested that they could replace this secondary mirror to reconfigure to another Cassegrain, F7 Cassegrain. That's this component here, this convex secondary, and you see it right here in the picture on the top end of the telescope. The price, $20,000. Okay, well, but you might ask, well, why F7? Why not F5 or 4 or 3? I mean, why not try and go faster? And so I went out and I did a design study and took a look at different Cassegrain designs. And here we are at our current configuration. And this is what the vendor suggested, 7. And you can see that, it's not too big. You increase the size of the secondary, you move the baffles around a little bit, and you wind up almost doubling the size of the field, okay? But let's be real here, all right, for a moment. Going from 0.2-ish to 0.4-ish is not really a very big field. And so we'd really like to be way up here, at 0.9, but we only got, 0.4. That's less than the size of the moon. So that's not great. And if you throw on top of that, look at what happens with the optical aberrations. You've increased the optical aberrations by 7 times in coma and 4 times in astigmatism. So that implies that you have to have a field corrector, and I doubt that they threw that in for the 20K. Okay, so you've got to go out and get that yourself, and that's only F7. If you wanted to try to go to 5, 4, or 3, look at what happens to the size of your secondary. It gets out of control. I'm not even sure if you could. Well, you certainly couldn't afford, the 19-inch secondary that would take to get to F3. And even if you did, we're talking about 2 orders of magnitude greater on the coma and the astigmatism that you'd have to deal with a field corrector. I'm not sure you can find a field corrector that would take care of that magnitude of coma. So 3 and 4 are probably out of the question for Cassegrains. 5 is a stretch. And that's probably why they stuck at 7. But you still need a field corrector there. Okay, so maybe Cassegrain, who knows? Maybe not. What about a Newtonian? All right, so you've already got the primary. It's F3.1. Going to Newtonian is just a matter of folding the optic with an elliptical flat. And so I went out and I did a design trade study on this. And basically what it boils down to is smaller secondaries wind up giving you more light because they don't obstruct the light path coming in, but they don't catch all the light from the cone coming back. And so you wind up having this drop off here. The trade space is to keep as much light as you can coming into the image, but you need the off-axis light to be even so that you don't wind up, seeing funky vignetting. And so 6, 7, 8, and 9-inch optics were played, and the sweet spot is about 8 inches. All right. So, okay, let's talk about that 8-inch option. So you just remove the secondary that's already there, and you replace with off-the-shelf components. An 8-inch elliptical flat is only a couple $1,000. The 4-inch corrector and 4-inch focuser, a couple $1,000 more. It looks like we're heading in the right direction. You have to cut a hole in the side of the OTA, okay? Somewhere in there, you got to place that, that focuser and the corrector. But, and I'm going to give you the spoiler alert, the optical performance is not as good as prime focus. So, and on top of that, you got some awkward stuff going on, all right? So think about, right now, this OTA expands and shrinks as a function of temperature, okay? But the optics are designed to float on these INVAR rods that are here. They're not, the spider is not connected to the OTA. It's floating on that INVAR rod, and so it's not moving while the OTA is moving. So if you punch a hole in the side of that OTA, the OTA is going to be moving, and that's going to move your focus position, right? Because you're changing up and down. You're changing the position where the focus is coming through. So you could ditch the INVAR rods, okay, but that's a really nice feature of this telescope. That's really nice. You could use this focuser to, inverse, to do the inverse of what the INVAR rods are doing and get back to the same motion as the OTA, but that's like getting rid of the INVAR rods. So that's ugly. And now you've got this focuser that's moving as the forks rotate, right? So it's moving in position up and down, it's rotating with the forks. That's kind of funky. And then you've got this issue of, well, are you going to stop down the eyepieces because you put a 4-inch focuser on there? Are you going to stop down the eyepieces? This can be done. Okay, this is an option. It would work. You could make it work, but I think we should set it aside for a moment and maybe look at the prime focus option. So I went out to the vendor almost immediately when I learned about this gift, and I started looking at their site, and I found what they call the prime focus instrument module. And I brought this up and I said, hey, this is what we really should be thinking about. At least I'd like to learn about, what the cost is, and hopefully they're reasonable about the cost of this thing. So they've replaced the focuser mechanism and the mirrored surface, okay, the convex mirror, with a lens assembly, all right, and a new focus plate. But as I was worried about it, okay, I heard that the answer came back that to go to F7 was $100,000, okay, and I balked at that immediately and said, no, this is not gold plated, okay? For those of us who know anything about optics, there are 3 lenses here, 1, 2, 3. And 3 lens optics are well-known design. Okay, that's a Win corrector. This is a commercially available component. And the focus plate is just a simple focus plate. Okay, that's a linear stage. So why is it $100,000 for a Win corrector and a focus plate? And so I thought, well, I'd rather just go out and look. So in the option of do-it-yourself F31 prime focus options, I started with plane wave. I thought, you know what, let's just go out and see what a plane wave telescope sells for a corrector. And I found a F425 corrector. It doesn't fit our telescope, but that's not the point. The point is that it's only 13K. So that tells you that there should be some other options out there. So that gave me hope that I could find something else. And I went and I found a French company, Alcor, that has a Win corrector. They had a design, okay? They don't have a product that they sell, but they had a design. And so I started working with them, and I worked with them for a while. And I sketched out how the design would work. And basically what happened was I ran out of back focus. I couldn't make it work because the size of this barrel is too big in comparison to the focuser. And so by the time you add the focuser in there, you've taken up all your spacer, and now you can't make the back focus work. So I talked to them and I said, hey, can you reduce the size of this barrel? Then I could insert it into the focuser. And they said, no, we don't want to do that, because that would, in the very largest frames, like medium format or even bigger, you would get some obstruction of the light path. And I said, but we're only probably going to use this with full frame. And they said, no, we prefer you to think about designing a custom focuser for this barrel. And that will fix the whole problem. And I said, well, I don't want to design a custom focuser. I'm already designing a custom prime focus, right? So I left off that and I looked some more, and I found an Italian company that sells an actual product. You can go out and you can see this on their website. The optic in here is about 6 inches and change, but it has the same problem, okay? It's got a big rear barrel, and bigger than I can fit in the largest focuser I could find, a 4-inch focuser. And so I talked to them about the same thing and came to basically the same conclusion, except that they said, yeah, they would reduce the size of the barrel if I was going to use a full frame camera and do a one-off on this design so that we could make it work. And as of about 5 months ago, I had spec'd out all the parts and pieces, the adapters, everything from precise parts to make that function. The specs, okay, all of these designs, by the way, I've looked at in terms of the ZMAX performance, and prime focus looks like the best option in terms of specs for both field illumination and spot size overall. And so I think this is a good place to be. Okay, so to take an entire talk, all right, that was a different talk on this particular option of how to put this all together, and to reduce it to one slide, all right, I'm going to tell you basically what happens. You take the existing focuser housing and you replace it with another housing of the same size so that you can mount the spiders. Then you stiffen the barrel with some annular rings here, okay? And one of those rings is pretty big so that you can actually mount the focuser to that ring. And then the optics are inserted into the focuser. On the backside of that focuser, a spacer and the camera is mounted. And what the whole thing looks like is this. And I don't know if you guys can see this motion. Hopefully you can. But this is the actual motion of the focus, okay? So you're not really moving very far with this to achieve focus. Can you guys see that or not?
Yep.
Okay, great. All right. So as I said, oh, and by the way, that design is less than 1/5 of the cost of of the original prime focus instrument module. So reasonable. All right, so I want to spend a moment on cameras because the decision for whether you do one-shot color or mono filters is not a no-brainer. If you're just thinking about pure simplicity, the advantage goes to one-shot color for sure. But you're giving up something for that, and you're giving up functionality in the way of isolating wavelengths, in particular HA, let's say. And you're also giving up imaging in moonlight. So if you wanted to add functionality and you want more efficiency, okay, better use of the telescope, it might be that mono and filters are the way to go as opposed to OSC. This is TBD, but it's not a no-brainer. I looked at several cameras, and to me, the sweet spot looks about to be an IMX 455 sensor. And the reason for that is that it has some really nice binning configurations which match the sight seeing. I think that that's important. And what you can see is in a bin 2 mode, which is kind of the normal CAC seeing mode, you would have 0.63 arc seconds per pixel, and the field size is 0.83 degrees by 0.55 degrees. Here's a picture of what the the field looks like. So you've got a bit better than the full moon with a full frame, and it's got a nice deep well. So I think that is probably about where the sweet spot is. So a little bit of trivia. The design spot size is about 5 microns. And that's a good size. That's a good match to the camera pixels. But remember that you're never really going to achieve the design spot size because you're always going to be seeing limited. And so for the seeing that you're going to get in the very best seeing at CAC, you could use bin 1 at 0.33 arc seconds per pixel and be Nyquist sample. For the normal seeing, 2 arc seconds or worse, you're probably going to want to use 0.63 arc seconds per pixel and you're still going to be well sampled. So this is not a hyperstar, but it's a lot like a hyperstar, just not quite as fast. And the critical focus zone is still tight, 100 microns at 2 arc seconds seeing. So that's manageable, okay? But you don't want to be, you don't want to be loose with your focus. You want to kind of keep it tight. And so automating the focuser is probably a good idea. The one thing that's going to help you is that the INVAR rods that are there should probably reduce the need for focus updates because you're not going to be quite as temperature sensitive. Okay, so I'm going to start to wrap this up, and I'm going to talk about the obstructions. If you look at the mirror, the old 13.6 secondary baffle is right here. Okay, so that whole area, basically, this is your clear aperture between the outer edge and the baffle. The new, if you went to F3, you would wind up, I see my connection is unstable. Here we go, we're back, I think. If you go to F3, you wind up with a much smaller, the housing, the focus housing is much smaller. And so the new optics housing would give you a little more of that light path back. The focuser electronics is going to stick out a little bit. And if it turned out that that was problematic for the PSF, then you would just baffle that off, okay? You would just mask it off. This hatch design down here represents what would happen if you put a 5-position filter wheel on the telescope at prime focus. And notice that that still fits within the envelope that the old secondary baffle had. So this is not too bad. What wouldn't be very good is to try and fit a 7-filter wheel on, 7-position filter wheel on. If you just avert your vision and look at that, you can tell the PSF is not going to like that right away. And so I wouldn't recommend trying to go to a 7, but a 5 might work. And again, both of these, if it turned out that the PSF was a little bit weird, you would just go ahead and put a baffle on top of that area. Okay, to finish up a little bit here, the primary aperture that I talked about for planetary use, I just played the game with the as-is of size of the secondary at 13.6, and you can get a 10.5-inch unobstructed aperture that would reduce from what I calculated to be 50 plus air cells down to something less than 10 air cells by doing this clear aperture, 10.5-inch aperture. If you were doing F3 with a closer baffle, you could probably get to almost 12 inches, and that would be clear aperture. So that's not a bad configuration. Okay, so let me wrap up. To think about this and expect the telescope to underperform its potential if it's not reconfigured to match the site. The telescope needs to match the site, okay? And there's just no ifs, ands, or buts about that. We're 7 months in now, and we still don't have a use vision for the 32. I think that's problematic. And I think until you get that use vision, that longer term use vision, you can't really make good technical decisions to maximize the value of the gift. And so, that has to happen. And and I say if, okay, the big capital if it becomes desirable to modify the telescope optics, folks should know there are multiple viable options, okay? Some of those options are easier than others, and I think all of them would need to be factored for risk, efficiency, and overall value before the changes are made. So I'm going to leave you with a picture and a thought, a thought that I want you to think about, and that is, here's a picture of M33 that was put out by Adam Block, I think like last month, okay? It was taken at Mount Lemmon using their 32-inch f7 telescope. It's a broadband RGB image with an HA overlay. So for us to reproduce something like that, we would need the 5-position filter wheel. I went and calculated the resolution of this image, and it's about 1 arcsecond, which is within reach, okay, of CAC, especially if you consider Blur Exterminator software on the back end. Now, Mount Lemmon has better seeing than we're going to have at CAC, okay, and that's to be expected. They're at 9,000 feet, okay, we're at less than that. So, but this is not to say that we can't produce this, and in fact, CAC has a darker sky. And if you want to think about comparing two 32 inches, one that's f7 and one that's f3 side by side, this image can be captured in 5 times faster than they captured it at Mount Lemmon. Both of them are mosaics, by the way, but that's beside the point. F3 is going to beat f7 every time when it comes to integration timing. So with that, I would ask you guys to go ponder this, go re-look at this video after it's done, think about those charts and ask yourselves, what would I do with the 32? And with that, I'll leave it for questions.
Doug, what was the original intended use for this instrument by the original contractor? What was that purposed out to be? And is that something that could be a starting point for using this instrument before directly and quickly modifying it?
Well, the second vendor, okay, the one that was purchasing it, was going to use it for satellite tracking. And the first vendor, the actual contractor who made the telescope, DFM, it sat in his backyard for a while, but I suspect that he was intending it to be used for research purposes, small universities, probably either with a camera, spectrograph, or polarimeter on it.
Okay.
So in that regime, if you will, that's a pretty broad spectrum of of potential use cases. And so I don't think we should try and guess what they were going to do there. But more than likely, this was not a visual telescope. It's really not meant to be visual, and more than likely, this would have had a camera on it. Of some kind or another. F-13, you can imagine a scenario where research, this is an older kind of telescope. If you look at Z, okay, in terms of the universe, this is going to be for smaller galaxies. You're going to get highly magnified views of very small galaxies. And, ideally, it's a little bit older. Nowadays, they put adaptive or active optics on these telescopes. But without that, you're not going to be doing cutting edge research, right? This is clearly graduate student level research.
Okay. The other quick question was, you talked about all the optical configurations that are possible. What about the mount itself, the tracking, the quality of the gear train, the ability of the mount to handle any imaging activities of the type that we're discussing here?
This mount is well designed. It's a friction drive. It can handle satellite tracking, and if it can handle that, I think it can handle your average DSO just fine. So I don't think that we have to worry at all about the quality of the tracking. I would say that maybe putting the telescope back together is the biggest risk factor there, because the weights on the telescope, you need to fine tune those torques on the weights to make sure that the tracking is not, amping out those drives. But I'd say once you do get the weights tweaked up and the torques right, then yeah, that's really not going to be a factor.
Yeah, absolute encoders, doesn't it?
It does have absolute encoders, yes.
What's the cost of this, I'll say hyperstar-like lens that you've been envisioning?
Yeah, so I think the lens itself is on the order of 15K. And, by the time you add the camera and the precise parts, flanges and what have you, you're looking at probably, by the time it's all said and done, everything less than 25. I think probably 20 to 25 is a very good guess for today. Now, how that factors as inflation goes up is anyone's guess, right? But
and where does oh, go ahead.
No, go ahead. Yes.
Well, where does Star Arizona maybe fit into this? I mean, they've got a design for a similar type of lens on a much smaller basis, but have you approached them to see if this is something they can make?
I didn't, because I presumed that the hyperstar configuration would not, the size of their lens. Okay, remember the lens element is 6.25 inches or so. That's a pretty big optic, and I don't think that Star Arizona makes. I think I did go look at the sizes of the hyperstar, and if I remember correctly, they were well beneath that size. So I don't think they make anything that's that big.
No, they don't make anything that big, but they can make. I mean, they manufacture stuff, so that's what I'm asking is whether they might be
to
a
think
potential.
About. Right. I wasn't so concerned with actually picking a vendor as finding a viable option, right? I was trying to get to a place where we were spending less than $100,000 for a gold-plated focuser. Yeah.
Yeah, that last idea, I'd like to share that. I think that last idea is the one we should go with. And that I think that camera would be that 6200 would be ideal. And those cameras have a good dynamic range. And
no, it does. It's got a nice deep well and bin to mode. I mean, that really is a sweet spot for that site and that telescope. Yeah.
yeah,
Especially if you go down to F3,
yeah,
you're in the right spot. So that's what I'm talking
absolutely.
about, designing an optical system, right? You don't want to just take what you're given. You really want to think about, what is the site giving me in terms of seeing, and what does this telescope provide, and how do I get to the sampling that my seeing is going to give me? Once you match those three together, you've done your homework and you're ready to go.
Yeah. I think this is the way to go, really. Those other ideas are, I think we should stick with prime focus. And, we have plenty of visual telescopes. And, a Dobsonian, by its very nature, is a dedicated visual scope. You can't use it for, except for maybe the moon or the sun. I mean, and it's something that takes an instantaneous exposure. You might be able to use it for that. But, I mean, we've got plenty of them. We've got the 40-inch, we've got the 18, we've got a 25, I hear. And those will not be suitable for imaging. So I was kind of thinking it was time that we had a scope out there that was dedicated to just imaging. And then people could get time on it, from time to time. And it's
Spoken
just,
from a true imager.
yeah.
Doug,
Well,
I've got a question for you. This is a monochrome camera that you've been discussing, and I understand the benefits of the monochrome.
No, actually, it's either or. You can get this camera in OSC or in monochrome.
Okay. Oh, what in an OSC configuration then? Let's say if we had both the color and the OSC cameras, would it be how difficult would it be to swap them between them?
well,
Well, I would recommend that probably it's a good question. I don't think it would be too complicated because, again, you're just screwing this on to the back. Okay, so
yeah, it just screws on like a light bulb.
exactly, it screws on like a light bulb, but
We don't
you
know,
would want to.
we don't know that for certain. His design might be different. You're talking about the hyperstars. This might be different. That's why.
Oh, no, I'm not talking about Hyperstar. I thought you asked me about the camera.
No, I'm talking. I'm mentioning to Paul that this isn't necessarily a screw-on. The hyperstar is a screw-on. I'm asking you in particular because I want to know how that changes from one to the other.
Well, the cameras are both.
No, I'm not talking to you, Paul. I'm asking Doug.
Yeah, okay. So if you're asking me about the lens system, swapping out the lens, so let's talk about that for a moment.
No, not the lens. I'm talking about the cameras. If
the
you
camera,
color...
I specified, I went out and worked at precise parts to specify and find the actual flanges and their screw on. So this is not the problem. That camera has a screw-on interface, and you would keep the tip tilt plate on it, and it would just screw into the adapter. So there's a spacer back there. I can
relatively easily.
Yeah, relatively easily. But again, I think this is F3, and you want to be careful with the field. You've got a bigger field, and you want to pay attention. So I would think that a quick exercise to check the tilt of that sensor after you take it off and put it back on, would be appropriate, right? You wouldn't want to just assume that everything's going to be great. If you torque on that camera as you're screwing it in, you're going to affect the collimation. Yeah.
Sure. Okay.
But I'd say with reasonable care, you could in fact change the camera and go mono to
the reason I ask is I know that semi-professionally we know what we are doing. If you wanted to use this for outreach, if you had some dedicated outreach students in there, you wanted to switch over to a one-shot color just to make it more simple for them for the evening, that's why I'm considering it.
Well, one thing you got to consider, one thing to think about anyways, is in terms of complexity, changing the camera often requires you to do sky flats. Okay, you're not going to have a panel here that you can set the telescope down on the horizon and put a panel up for. You kind of need to do sky flats anyways. And so if you don't change the camera very often, you can get away, as long as you keep the optics reasonably clean, you can get away with not having different flats. And this is something to be thought about. I mean, the less you tweak that environment, the less you have to worry about things changing for the worse. And it's always for the worse. It's never for the better. So just something to think about.
Thank you, Doug.
Yeah. Anything else? Okay, I'll pass it back to.
Actually, I do have one question. So
Yeah.
we just mentioned flats. How are you envisioning that these flats would be done?
They got to be done with sky flats. I mean, there's no other choice. I don't see, the telescope is too tall to throw a t-shirt over, and you're not going to put a panel on the side of the building that it's in. It's too big, right? 32 inches. So I don't know, maybe it is possible. Maybe you can find a ginormous flat panel that you could throw up in the building, but I'm presuming that more than likely you're going to wind up doing sky flats for this, which isn't horrible. This is something that people have to learn, and it can be done. But yeah.
Doug, Adam Block has a big white screen that he illuminates indirectly, and it seems to work really well with the 32-inch Schulman.
Interesting, like a projector screen, yeah?
Yes, exactly.
Okay, yeah. I mean, if you could achieve the perfect illumination, right? It could get a little tricky there to achieve even illumination across that screen. But yeah, if you can do it, that would be fabulous, right? I mean, that would be way preferred over sky flats.
Would you mount a color camera right onto the filter wheel? Shoot through the clear filter?
You could do that, but if you do that, then what are you going to do? Take HA through the through the Bayer matrix? I mean, that's a little funky. Well, you could, yeah, but so there's options there. I think that you could do it either way. I just love that picture. That's the best picture of M33 I've ever seen, and I think that there's something to be said for that kind of quality. I can imagine, TAAA putting out a picture of the month or something, where we did something special with that. But again, I don't want to presume. I think we're coming back to the issue that I brought up, which is that there's no defined mission for that telescope yet. And until we decide that, we can't figure out if we need an eyepiece or not. If we want to ditch the eyepieces in visual use, you go to just imaging, then you've got another possibility. But all of this kind of hinges on what do you intend to do with the telescope. Once we know that, you can make good technical decisions to get the most out of the telescope.
Okay, well, great. I think you've given us a lot to think about, a lot.
Yeah, and I'd say go back. For those who haven't seen it, I recommend go back and look at the video again. Check out those charts after the fact and convince yourself one way or the other what you'd like to do with the telescope. And then let it be known. Right. All right. Thanks,
Thank you for all your efforts, Doug.
Yeah, thanks, Doug. I mean, you put a lot of work into this, and it's obvious from what you've presented tonight that you've done it with a lot of thought. So thank you.
All right, great. You're welcome.
Ed, do you have anything else you'd like to add?
Yeah, I would. Doug is right that the mission for this telescope has not yet been written. We're taking it a step at a time. Putting it in place is the first step, and it is, as Doug pointed out, it's a risky step to reassemble this. We want to make sure that it's operating well before we consider the next step. But what we don't want is to stray from the fundamental mission of TAAA. So bear that in mind when you consider any of the changes that we'd be looking at. We're looking to make sure that this is an instrument that members are going to be able to use. And so as it is written, it will be written with those fundamental tenets of TAAA in mind. And it won't be done in a vacuum. We already have called on many members of TAAA to be involved in this effort. And all of you who know Doug, he's one of the experts that we call on. And it's that kind of expertise that gives us comfort that when we end up in the final phases of putting this telescope in place, that it will be the best telescope that site will be able to use. We've got a lot of talent that is being drawn on to both build it and to ultimately configure it and wait until we get it remote. It looks like it could be a very, very special instrument for the organization. So stay tuned. This group here is one of the groups that will know the aspects of imaging that we're going to be looking at for phase 2. So when Doug asks you to think about this, please think about it, because you're going to help us come to the right conclusion when we get to the next phase.
All right. Any other questions for Ed or Doug?
I have one, and this gets, if we end up going down this path of putting, an optical, a camera system on it, what would be guiding it? What would be, and maybe my question is not what would be guiding it, but what would be running it? Would it be something like Nina? Does it interface to it, or what would be the process of operating the telescope? That's for Doug or Ed.
It's probably for Doug.
Well, immediately, the telescope has its own control X, as Ed mentioned early. It also can run. It has an interface for ASCOM, and so there are other options as well. And since I'm switching over to Nina, I think the idea of Nina is interesting. But there's also a longer term vision where when you go remote, it may actually be that you can simplify the interface quite dramatically by just providing a script interface for the kind of exposures and times and what have you that you want. So I've already been looking at that. I provided a paper by the University of Wyoming on what they did to make their telescope remote. And looking at that interface, there are options there to simplify the overall driving of that telescope in remote operations. And that's something that will come later. But yeah, it'd be fun to have Nina driving that telescope remotely, wouldn't it?
I got something to add here too. I just did a calculation. You said that's an f3.11, right? That primary?
That primary, yeah.
Yeah, okay. It comes out to 2,500 millimeters and some change.
For F3, yeah, right.
Okay.
Exactly. That was in the chart, by the way.
So I figured out what the true field on a full frame, a 24 by 36, it's 32 by 48 arc minutes.
I don't think that's actually true. Why don't we talk offline, and I'll try and show you the simulator that I used to figure out the field. It's bigger than that. Yeah, it's actually bigger than that.
So? Okay.
Yeah, I do. Yeah, but we can talk about that separately. I'll send you an email and we can chat.
Uh-huh.
All right. Well, any other questions or images for discussion? All right. Well, thank you all for joining us tonight, and I'll try to get this recording posted as soon as possible so you can review it at your leisure. Thanks a lot, and we'll see you next month.
Take care.
Yep.
Good night now.